All right, 9.5 is about vectors in a plane. So we're going to start with some reminders about what a vector is, some notation and different things, and then we're going to tie the idea of a vector basically to a parametric equation and look at the calculus surrounding that. So let's start just by redefining a vector. A vector is a representation of direction and magnitude. Direction and magnitude, so it's in a length and a direction, right? Vectors are a line segment that span 2 points in a given direction. If we went back to geometry, we probably wouldn't use the word vector, we would use the word ray, but it is finite. It has a length and a direction. The component form of a vector is really just that v, or sometimes you'll see the little vector symbol on top, but not always, is equal to the x value and the y value, and we use these little triangular brackets, I don't actually know what those are called, little greater than, less than symbols, to represent that we're talking about a vector. I'm actually going to skip down to magnitude next. The magnitude of a vector, which we use what looks like absolute value symbols to represent magnitude, is equal to the square root of x squared plus y squared, right? We're finding the length basically using the Pythagorean theorem to talk about the magnitude, the length of our vector, which leads us to trig form. We could also represent this as the magnitude of v times cosine of theta and the magnitude of v times sine of theta. When we're talking about the direction, we're really talking about theta. We're talking about the angle. And if you remember from earlier in this unit and in previous classes, we know that tangent of theta is equal to y over x. And this could just come from the idea of a triangle, right? This is y, this is x, this is our vector here. Since tangent of theta is equal to y over x, we could say that theta is equal to inverse tangent of y over x. Something to keep in mind is that we're going to be representing this angle positively. So occasionally you will see this with absolute value around it, but really what you just need to keep in mind is you need to keep the quadrant in mind. Keep quadrant in mind. And what I mean by that is you may end up needing to use angles that are equivalent, but maybe that are 2 pi more, that are represented using reference angles. So you may have to use reference angles to talk about the angle in a positive way, and we will be working through that today as well. Equivalent vectors are just any vectors that have the same magnitude and direction. Same magnitude and direction. So let's just quickly review. Using this example over here, we are given a vector from the point negative 3, 2, which is A, to 4, 1. So go ahead and graph this vector. We're actually going to graph it first. And maybe I should have picked a darker color there, but you can see that this is traveling from the point A on the left to the point B on the right. Now, if we are going to write this in component form, we need to talk about, okay, well, what is our x distance and what is our y distance? So our y distance to get from point A to point B, and actually I'm going to zoom in on this graph. To get from point A to point B, our change in y is just -1. To get from point A to point B in the x direction, this is going from -3 over to +4. That has a length of 7. So the vector in component form would be equal to our x value, 7, comma, our y value, -1. And you could calculate this change by hand, but really you're just asking yourself, what am I doing to -3 to get to 4? Sorry, what am I doing from -3 to get to 4? What am I doing from 2 to get to 1? And that's where these numbers are coming into play. So we graphed this already. Find the magnitude. So the magnitude is going to be the square root of 7 squared plus -1 squared, which is going to be the square root of 50. No need to simplify that radical. We're in calculus. We don't have to do things like that anymore. Oops, I just did that in the wrong spot. Find the magnitude. We just did. The magnitude is the square root of 50. Find the direction is going to ask us about theta. So we know that tangent of theta is equal to y over x. So thinking about what quadrant this is in the second quadrant, just keeping that in mind. And then on your calculator, you can actually just hit to figure out what this is. This is going to give you negative 0.141. The problem is that we want this angle to be positive. So thinking about where this is, and what I mean by that is if I graphed this vector in terms of the vector, the component form 7, -1. So that would be out 7 in the x direction, down 1 from the origin. Thinking about this in component form, what we just calculated was this angle right here. But what we want is a positive version of that angle. So we want to think about going all the way around and getting that angle in a positive way. So what we can do is really just add 2 pi to that. In this case, that would give us the equivalent vector with direction. So you can do that on a calculator. You could also leave this as just negative 1.41 plus 2 pi, but this is really telling us that theta is actually going to be equal to 6.141. So again, the why we did that is because we want theta to be positive, not greater than 1. We want theta to be positive. So sometimes we have to manipulate the angle to be actually talking about a positive theta. So, and this was just really how I was thinking through it, what I needed to do to get a positive angle in my head. And then the last part of this question is asking us to rewrite it in vector form, rewrite the vector in trig form. So that would give me the magnitude is the square root of 50 times cosine of, what did we just find out theta was? Cos theta was 6.141 times the square root of 50 times sine of 6.141. And there we have it. We rewrote the vector in trig form. In calculus, it's most often that we're talking about vectors in relation to position, velocity, and acceleration. That's right. It has not left us. We are still talking about it many, many units later. So the position vector would just be s of t, which is just x of t, y of t. Velocity is just the derivative of position, which would be x prime of t, y prime of t. And acceleration is just the second derivative of position, or the derivative of velocity, which would be x double prime of t, y double prime of t. Speed at a specific time, so let's say at t equals, not 3, t equals c, that would just be the magnitude of the velocity vector at that particular value, which would be the square root of x prime of c squared plus y prime, that looks like a G, let's try again, y prime of c squared. And then the distance traveled would be the integral from some t1 to t2 of the magnitude, or of that speed, dt, which we could rewrite using what we just defined the speed to be. So we could rewrite it just like that. And when are these vectors at rest, or when is a particle moving along one of these vectors at rest? That would be true when the velocity is 0, but something to notice, the velocity is made up of both x and y components. So we need a t value that makes both, and this is the big part, both x prime of t and y prime of t equal to 0. They both have to be 0 in order for it to be at rest, because it's possible that it's not moving in the x direction, but it's moving in the y direction. So we need both of those two values, or one t value that makes both x and y, the first derivatives, equal to 0 at that particular t value. All right, let's go ahead and look at some examples now. Okay, given the position vector for a particle that you can see there, find the following. So here is our position vector here. First, we're going to go ahead and graph it. You can make a table for t, x, and y, and you're going from 0 to 2, so you can go ahead and just plot when t equals 0, 1, and 2. So pause the video and sketch that graph. And there is the graph. All right, let's go ahead on part B and find the velocity vector. So we're going to take the derivative of the position vector. That's going to give me 6t. And the derivative here is going to give me 3t squared minus 3. And then the velocity vector, so I guess this is v of t. V of 1 would just be 6 times 1. And 3t squared minus 3 when t is equal to 1 is going to be 0. Find the speed of the particle at t equals 1. So we want the magnitude of the velocity at t equals 1, which is going to be using this vector that we just found. So 6 squared plus 0 squared. So the magnitude of the velocity at t equals 1 is going to be 6. Find the distance traveled between t equals 1 and 3. So we're going to be looking at the integral from 0 to 3 of 6t squared plus 3t squared minus 3 squared, integrating with respect to t. Let's go ahead and expand out the inside of that radical. This problem doesn't tell us to use a calculator. It could be a problem that was on a calculator section, but it doesn't ask us to use a calculator, so I'm going to see if we can do this by hand. So when we expand and then combine like terms on the inside we get here, we can factor a 9 out of the inside, and then when we square root that, we get a 3. So let's simplify this one step further. So that's going to give us 3 times the integral from 0 to 3 of t to the 4th plus 2t plus 1. Sorry, 2t squared plus 1 dt. And then that actually factors to be a perfect square, which then we can divide, or we can square root. So that's actually going to simplify to just be t squared plus 1 integrated from 0 to 3. Pause the video if you need to see that. You can factor this. Whoops. You can factor this. And then that's going to simplify. So now we can just apply the power rule. So this is going to become t to the 3rd over 3 plus t evaluated from 0 to 3. So 3 times 27 over 3 plus 3 minus 0. And that's going to give us 36. So pause the video if you need more time, but I do think it's a good practice for you to work through that by hand. All right, part E says, find the time when the particle is at rest. What that means is we need to take x prime of t, set that equal to 0, find y prime of t, set that equal to 0, and see which t values in both of those give 0. So let's start with x prime of t. So x prime of t, or the x part of our velocity vector, is 6t. 6t is equal to 0, only when t is equal to 0. Let's look at y. Y prime of t is 3t squared minus 3. This is going to be 0 when t is plus or minus 1. So what I'm doing is I'm looking for now where there is overlap. What t values make both x prime of t and y prime of t equal to 0. And in this case, there is no overlap. And what that means is this particle is never at rest. It's never at rest because there is not a t value that makes both components of the velocity vector 0. Okay, let's look at the last one. We're looking for, and let's adjust this page a little bit, where the acceleration, what is the acceleration vector at time t equals 2. So let's find the acceleration vector first. We're going to take the derivative of this vector, which is going to be 6 and 6t. The acceleration vector at 2 seconds is still going to be 6, but the y component is going to be 12. Let's work through a few more examples together. All right, for problem number 2, I encourage you to pause the video and work through as much of A through F as you can on your own, and then unpause the video and see how you did. Really challenge yourself and see, do you really actually kind of already know how to do most of this, or do you need a little bit of help? Okay, the one thing I will remind you is don't forget about plus C when we're integrating. Don't forget your plus C. And you may have to use subscripts when you're doing this because you might be identifying multiple c values in different problems, right? Because each of these vectors has an x and a y component, which would have a different potential c value. So what in the world am I talking about? Let's look at this first. Part A says the velocity vector. So we're given the acceleration vector and we're being asked for the velocity vector. So acceleration vector is -2 cosine of t, -3 sine of t. The velocity vector is going to be what I get if I integrate the acceleration vector. So I'm not actually going to show the integration. These are pretty simple antiderivatives. So v of t is going to be -2 sine of t plus c1. For the y component, I'm going to get 3 cosine of t plus c2. Now I need to use the initial condition that we're given to figure out what my c1 and c2 values are. So when time is 0, -2 sine of t, when time is 0, the x component is 0. So -2 sine of 0 plus c1. This is going to give me that c1 is 0. For the y component, 3 equals 3 cosine of 0 plus c2. Well, cosine of 0 is 1, so c2 is also going to be 0. So we end up with the velocity vector -2 sine of t, 3 cosine of t. For the position vector, we're really going to work through the exact same process. To find the position vector, we need to integrate the velocity vector. We need to include different subscripts for our c values there, and then solve for those c values and rewrite our position vector. So go ahead and pause the video and work through that on your own. So s of t is the integral of v of t dt. In this case, if we are integrating or finding the antiderivative of -2 sine of t, that would be 2 cosine of t plus c3. Since I already used c1 and c2 on this problem, if I'm finding the antiderivative of 3 cosine of t, that would be 3 sine of t plus c4. Now I need to figure out what my c3 and my c4 are, and I can use this initial condition to do that. So when t is 0, the x component is 2 cosine of 0 plus c3. That means that c3 is 0. When t is 0, y, the y component is root 2 over 2 equals 3 sine of t plus c4. Not sine of t, sine of 0. Sine of 0 is 0. So c4 is just root 2 over 2. So my position vector is going to be 2 cosine of t, comma, 3 sine of t plus root 2 over 2. Part C says find the velocity, position, and acceleration vector, specifically when we are looking at a t value of pi over 4. So velocity vector, well, I'm gonna go position vector first. I like to just do it in order. So S of pi over 4 is 2 cosine of pi over 4, 3 sine of pi over 4 plus root 2 over 2. And that is going to be root 2, comma, 2 root 2. The velocity vector evaluated at pi over 4. I'm going to skip the substitution step. -2 sine of pi over 4 is going to be negative root 2. And 3 cosine of pi over 4 is going to be 3 root 2 over 2. So there's my velocity vector. And last but not least, acceleration at pi over 4. So I'm coming up here and looking at this. -2 times cosine of pi over 4 is going to give me negative root 2. -3 times sine of pi over 4 is going to give me negative 3 root 2 over 2. So now I have my 3 vectors. We're going to use this information on D and E, and there's a typo on E, but I'll explain that when we get there. D is asking us for the speed. Remember that speed is just the magnitude of the velocity, in this case, the velocity vector at pi over 4. So that is going to be equal to the square root of the x component squared plus the y component squared, which you can do a little simplification there and get that this is the square root of 13 over 2 is the magnitude, or sorry, is the speed, which is the magnitude of the velocity vector at pi over 4. The directions on E should say the direction of the particle at t equals pi over 4, which means that we should be using the position vector, and we're going to find out what theta is using the position vector at pi over 4. So tangent of theta is going to be y over x. So we're looking for when inverse tangent, or when is tangent equal to 2. That will give us our theta value. And you can use a calculator for this. This is going to give us that theta is 1.107. And this is obviously in radians. D is only asking us to set up. It's asking us for the total distance traveled between 0 and 2. So 0 and 2 are going to be our bounds on our integral. We're going to be taking the square root of -2 sine of t quantity squared plus 3 cosine of t quantity squared dt. And if you had to evaluate this, this is a calculator problem. You would just plug it into your calculator. So hopefully you're feeling pretty good about moving between position, velocity, acceleration, talking about speed, talking about the direction, meaning asking about theta or total distance. And if you need to, you can go watch that part of the video again. Let's extend this idea of position, velocity, and acceleration a little bit further into more of what we have been talking about in Unit 9. So let's look at this last example, number 3. A particle is moving around the curve r equals 2 sine of theta, such that for any time t, theta equals 2t. What's the particle's position, velocity, and acceleration vector? Let's start there. So notice that position is going to be a function of theta to start with, so we can go ahead and write this out, x of theta, y of theta, and then we can substitute in what we know, that x is equal to r cosine of theta and y is equal to r sine of theta. And here is our r. So our position vector, s of t, is going to be equal to 2 sine of theta cosine of theta, comma, 2 sine squared of theta. However, right now, this is in terms of theta, and we need to move this or modify this to be in terms of t. S of t is a function of t, which means we need our vector to be in terms of t. So we're going to substitute in 2t for each of our thetas. So that's going to give us that S of t is 2 sine of 2t cosine of 2t and 2 sine squared of 2t. And this is fine for our position vector. Since we're going to have to take derivatives here, I'm going to use a trig identity to rewrite this just slightly. Actually, I'm going to use this green color to rewrite this. This is the same thing as sine of 4t, using the the double angle property, but using it in the reverse way that we normally use it. And the reason I want to do this is it's just going to make it much easier for me to take derivatives, which is what I'm going to have to do for velocity. So this is another way to represent position. You could leave it like this. You're just going to have a lot of chain rule and product rule situations happening with that derivative. And since it's avoidable, I'm going to manipulate it in that way. Okay, so let's find our velocity vector. So we're just going to take the derivative of this. That's going to give us 4 cosine of 4t. And 8 cosine of 2t sine of 2t. Applying the chain rule there. There's our velocity vector. And we could simplify this as well. This is 4 cosine of 4t. And I could simplify this part, I'm going to do this in green, to be 4 sine of 4t. You do not have to use these trig identities to simplify. You're just going to be working with messier derivatives, which may not be a problem for you, and it's good first semester review. So now I'm going to take the derivative of this to find the acceleration vector. That's going to be negative 16 sine of 4t and 16 cosine of 4t. And now I have satisfied this first part, position, velocity, and acceleration vectors. The last thing that we're being asked here is, what is the total distance the particle traveled between time 1 and 2? So we are going to integrate from 1 to 2, and we're going to integrate our velocity vector. So here is that integral, and then you can find that answer on your calculator. I believe that that should be 1.170 for our total distance. So key ideas from this section, just a little bit of review about what a vector is and how it works, what component form it is, what trig form is, how to find the magnitude and the direction, what it means for vectors to be equivalent, how to graph them. So that was mostly review, and then extending that idea to position, velocity, and acceleration, and looking at that from the sense of a particle. So looking at that parametrically in terms of vectors. If you have any questions, make sure you write them down as you go and bring them to class, and I look forward to answering those questions and working with you in class. Thanks for listening.